Okay, let's start. So now see how to prove the theorem. How to prove the theorem. So in this case, we have three cases. We have three cases to prove the theorem. First one need to prove for positive integers, and need to prove for negative integers, and need to prove for rational numbers. Three cases. Okay. Then again, we use theorem to prove theorem again. We use same theorem to prove the theorem. Special property. Okay, now see this one. Proof of limit x goes to a, x to the power n minus a to the power n divided by x minus a equal n minus 1. Proof of this. Proof of the theorem. Now case 1 for positive integers. Case 1 for positive integer. Of n. Positive integer of n. Okay. Now see this one, factorization technique. So if you have x to the power 1 minus y to the power 1, we have factor x minus y, no? Then x to the power 2 minus y to the power 2, we have factor x minus y, x plus y. X plus y. Then x to the power 3 minus y to the power 3, x minus y, x square plus xy plus y square. Then x to the power 4 minus y to the power 4, x minus y, x to the power 3, x square y, xy square y cube, no? See here, power 4 we have factor x minus y. Start with power 3, x power decrease in y power increase in, all are positive. Then here power 4 we have 4 terms, power 3 we have 3 terms here inside this bracket, no? Then as x to the power n minus y to the power n, x minus y, x to the power n minus 1, x to the power n minus 2y, y to the power n minus 1. That's the pattern. So x power decreasing, y power increasing. Or within 2 terms, positive here, the bracket. Then we know here number of terms n. Here for 4, number of terms 4. For 3, number of terms 3. For 2, number of terms 2. Then for n, number of terms n, no? Number of terms n. Then according to that one, we can factorize. Okay, now let's move to this. Let's move to this one. Now for positive integers. See. Limit x goes to a, x to the power n minus a to the power n of x minus a. Limit x goes to a, here x minus a, x to the power n minus 1, x to the power n minus 2 y, x to the power n minus 3 y square, it goes like that, y to the power n minus 1. Not y, no, that is a. Here into a square, here a to the power n minus 1 over x minus a. Now cancel this factor. Now we know here there are n number of terms. No? Thereafter, after cancelling this factor, that undefined case has gone. It has gone now. Then you can substitute. Substitute a to the power n minus 1, a to the power n minus 2 times a to the power n minus 3 times a square. It goes like that. A to the power n minus 1, you have to put at least 3 dots here because it is a series. No? Now, when you check here a to the power n minus 1, here add indices, again a to the power n minus 1, add indices, a to the power n minus 1, so on, a to the power n minus 1. Then all terms are a to the power n minus 1 terms. We know here number of terms n. Then similar type n terms, no? Then finally n into a to the power n minus 1. A to the power n minus 1. Then na n minus 1. That is the proof of for positive integer. This is for positive integer, not for negative integer and rational number. Okay, do that proof. If you need to write this one, you can write. If you need to write these factors, I have given this one before. But if you need to factorization, just write this by the side. Then do this proof for positive integers. Okay. Now for negative integers, see this one. For negative integers, case 2, for negative integers, okay? Then for this case, now we have done for positive integers, no? We have done for positive integers, here positive integers. Therefore, when proving for negative integers, the positive integer proof you can apply. Positive integer case proof we can apply, okay? Now, here limit x goes to a, x to the power n, a to the power n, x minus a, divided by x minus a. Then we know now here n negative integer, no? N negative integer. Then n negative integer mean you take here n value equal minus k. Say k positive integer. When k positive integer, k times minus 1 mean negative integer value, no? Negative integer. Then limit x goes to a, instead of n put minus k. Limit x goes to a, then here minus k, no? 1 over x to the power k, 1 over a to the power k, x minus a. Then minus power mean take downstairs, change in sign. Then get common denominator. Limit x goes to a, here x minus a in denominator, x minus a in denominator, and take common denominator, that goes to again downstairs, x to the power k, a to the power k, and here this goes to a to the power k and x to the power goes to other side. Here it is now. Okay. Now k mean positive integer, no? K positive integer. Then positive integer proof we have done previously. Therefore you can directly apply for that. Then I'll write this one. Limit x goes to a. So I'll rewrite, separate this part. 1 over x to the power k, a to the power k, into limit x goes to a, change minus outside, put minus here, and interchange these two. X to the power k minus a to the power k over x minus a. X to the power k, a to the power k over x minus a. Interchange these two and change the sign, and denominator, this part you separate. Now here k mean positive integer. For this part, positive integer proof we have done, no? Then apply theorem again. For this case you can substitute minus 1, put a to the power k, and for this apply theorem n minus 1, like this. For this part, apply theorem. We are still on the way of proving that theorem, but anyway, you can take that because for positive integer, partially we have done. The positive integer proof, take. Now simplify. Minus k, a to the power k minus 1 minus here, same basis now. Then minus k, take these two upstairs. Then minus k, a to the power minus k minus 1. Then minus k mean n, no? Then say n minus 1. n minus 1. Instead of minus k, put n now. That's how we prove. Do it. Okay. Now we have done proof for positive integers and negative integers. Now for rational number. Then again, we have done for positive integers, negative integers. Then for rational, you can take both. Okay. Therefore, when proving this theorem, we have three steps, and we use same theorem again and again to prove the full case. Okay. Now let's move for rational type, rational number. See this. See this one clearly. Rational number. Okay. Here let n equal p divided by q, pq integers, q not equal 0, and pq doesn't have any common multiple. Here rational thing. That's the rational thing. Okay. Therefore, you take n value like p divided by q. Then for rational number, we have property, no? We have properties. P divided by q type. See clearly. Then limit x goes to a, x to the power n, a to the power n of x minus a. Limit x goes to a, now x to the power n mean p divided by q. Further, limit x goes to a, I'll do this, say x to the power 1 over q to the power p. Here this power take outside. A to the power 1 over q to the power p, x minus a. Okay. Then I'll use substitution. Let x to the power 1 over p equal capital X. I'll take this one as capital X. And a to the power 1 over q, here 1 over q, x to the power 1 over q, a to the power 1 over q, you take capital A, 1 over q, capital A, 1 over q. Now, you put here, then by this one, you take power q, simple x equal x to the power q, simple a equal capital A to the power q. Then put capital X here, capital A here. Limit simple x goes simple a, here capital X to the power p, here this is capital A to the power p. Simple x mean x to the power q. Simple a mean a to the power q. Now that has converted up there. X to the power p, a to the power p, x to the power q minus a to the power q. Okay. Then further, okay, I'll go a little further. Check this. Now, up to now we done limit x goes to a, simple x goes to a, x to the power p minus a to the power p over x minus x to the power q minus a to the power q. Then by this substitution you say as x goes to a, capital X goes to capital A. Okay. Here as x goes to a to the power 1 over q, then a to the power 1 over q mean capital A. Therefore, as x goes to a, capital X goes to capital A. Then you change this limit, capital X, capital A. Then now divide by x minus a, both upstairs, downstairs, and separate limit. Like this. Now p mean positive or negative integer? No? P mean positive or negative integer. For positive integers we have done, for negative integers we have done. Then apply theorem, numerator and denominator. P a, p minus 1. Here q a, q minus 1. Now we have to simplify. P divided by q, a to the power, here take this index upstairs, p minus 1 minus q minus 1. P divided by q, a to the power p minus q. A to the power p minus q. Okay. Then here p divided by q, take q outside. Then p divided by q minus 1. Now, initially, n equal p divided by q. Therefore, p divided by q mean n now. Then here p divided by q mean n. A to the power q. Here, a to the power q equal a. A to the power q equal a. Here for this part a. P over q n minus 1. That is for rational number proof. Then first you prove for positive integers, then you prove for negative integers, then you prove for rational type. Okay. Now do complete proof.